Hello everyone. Today, this is my honor to present our latest work, random spiking and the systematic evaluation of defense against adversary examples. I'm Huangyi from Purdue University. Currently, adversary examples has become a security issue in neural network-based classifiers. For example, given a benign image and a neural net model, usually it can make a prediction with high prediction accuracy. However, we can use iterative-based attack algorithm to add human invisible noise to generate an adversary example, which causes the model to make a misclassification. To deal with such adversary example, researchers has already developed defense mechanism such as enhanced training based on distribution, model hardening based on adversary training. Researchers also develop a detect algorithm to detect adversary examples such as magnet. We can also use region-based classifier to generate multiple small variants to the benign image and use majority voting to make a prediction. In this paper, we does not including other defense mechanisms such as feature screening. To generate adversary example, we can use iterative-based attack algorithms such as collinear and Wagon and deep4. We can also use first-order based method to attack neural network classifier, such as projected gradient descent and fast gradient method. In this paper, we use collinear and Wagon to generate adversary example. So far, we know adversary example should be close to benign images, which means the adversary image should not affect human perception, and it will also cause the classifier to make a misclassification. Researchers have already proposed many defense mechanisms and attacks. To better understand which defense mechanism give a better protection and which attack algorithm can generate more effective adversary examples, we really need a fair head-to-head comparison of different mechanisms. So in this paper, we first propose a new defense mechanism called random spiking. Then we also propose a systematic evaluation methodology based on model of adversary knowledge. We also showed that in a gray box setting, adversary can choose better attack strategy to generate more effective adversary examples. Let's first take a look at our defense mechanism, random spiking. Adversary examples occur because they fall outside the distribution of training instances. This vulnerability to adversary examples is a form of overfitting. Adversary can generate an adversary example on a white box model. Those generated adversary example is highly likely can be transferred to a model, a new technical model, which behaves similarly as white box model. If white box defense is unachievable, then one should inject more randomnesses in training to reduce transferability. We should also examine techniques for dealing with overfitting. Since dropout is a widely used technique in the training phases, and it can deal with overfitting. So our random spiking is inspired from dropout. Basically, we generate a dropout to have randomly injected noise during training. Let's have a quick review of dropout. Dropout is a hidden layer placed in the middle of neural network model. It randomly selects output neuron and change the output to 0. Random spiking behaves similarly as dropout, and we prefer to place random spiking layer near the input level. And we would also use random spiking both in training and testing. Instead of change the output neuron to 0, we use random noises instead of setting activation to 0. By using random spiking, we can simulate the interpretation of each training instance should be treated as a set of instances, each with some small changes. Random spiking can also simulate adversarial training, which make small perturbation on benign images. Since we use random spiking in the testing, which means in each prediction it would inject some random noises. So we choose to use Monte Carlo decision procedure, which behaves similarly as majority voting. For details, please read our paper. So by using Monte Carlo decision procedure, we are approximating the behavior of a model ensemble. To have a fair comparison between our random spiking with other defense mechanisms, we propose a systematic evaluation methodology based on model of adversary knowledge. The adversarial knowledge can be divided into white box, gray box, and black box, three different levels. In this paper, we mainly focus on white box attack and gray box attack. In the white box setting, the adversary has the full access to a targeted model. Basically, it has the full knowledge of the targeted model and the defense mechanisms. To evaluate the resilience of targeted model, we can measure how easily we can generate an adversarial example. Also, we can first make a prediction on a benign image, then add some human invisible noise on the benign image, and then measure how likely the prediction output does not change. And we call such measurement as model stability. On the gray box setting, the adversary does not have full access to the targeted model. However, it has a knowledge of everything other than actual parameter of the targeted model. In other words, the adversary knows the training data, defense mechanisms, training algorithms. So it follows Kirchhoff's principle. To attack such targeted model, the adversary can use the knowledge to generate a targeted model to generate a shadow model, which behaves similarly as targeted model. Then use the white box attack algorithm to generate the adversary example. Then test how likely the adversary example can be transferred to the targeted model. Since the more noise added on the benign image, the more likely the adversary example can be transferred to targeted model. So our evaluation is based on transferability versus degree of perturbation. In this paper, we also present that just to attack one single shadow model does not use the full potential of the knowledge in the gray box setting. So we develop three different attack strategies. For the most simple case, the attacker just attack a single shadow model and generate adversary examples. We call such strategy a single model attack strategy. The adversary can use its knowledge to generate multiple shadow models, then use the attack algorithm to generate an adversary example which can fool multiple shadow models. We call such attack strategy as multi-model attack strategy. If we want to generate the adversary example to attack the model deployed on the cloud, we may face rate limiting issue. Also, if we want to compare the effectiveness of generated adversary example, just test it on one single one targeted model is not fair enough. So we developed the following more advanced attack strategy by dividing the shadow models into three different groups: training, validation, and target. The adversary first use multi-attack model strategy to generate an adversary example, then validate adversary examples on the validation model set. Basically test how likely it can fool the model in the validation group. The adversary would only choose adversary example which can succeed against a certain percent of the validation set and use those adversary example to attack target model. We call such adversary example attack strategy as multi-model and parsing validation attack strategy. To evaluate which attack strategy is more effective, we evaluate based on the transferability versus degree of perturbation, which we presented previously. We did the experiment on 3 datasets, MNIST, Fashion MNIST, and CFAR. And we group adversary example has similar L2 distance together, which present in the x-axis, and the y-axis represent the transferability. Here, we can clearly see multi-8 and parsing 5 out of 7 validation attack strategy achieves the highest transferability. Next, we did the experiment to evaluate our proposed defense random spiking. Here we can see on the 3 data set, it caused a 1 to 2 accuracy dropout by using random spiking. And we compare our defense mechanism with other defense mechanism by measure the model stability. In the white box attack scenario, we measure the amount of L2 noise need to add on the adversary example. In the gray box setting, we evaluated the transferability. By measuring the model stability, we first make a prediction on the benign image, then we add human invisible Gaussian noise on the benign image and measure how much percent of prediction does not make a change. And we plot the added noise in L2 distance on the in x-axis, and the unchanged prediction is plotted on y-axis, and we can see random spiking give the highest model stability. This behavior presume if we use JPEG compression as image preprocessing method. As the compression rate increases, prediction stability will drop. But random spiking still give a higher level of stability over other mechanisms. Even if the compression rate is extremely high, but random spiking still gives the highest relative high model stability. In the white box setting, we measure how much amount of L2 noises are necessary to generate an adversary example. We first use single attack strategy. Here we can clearly see random spiking require more added L2 noise to generate adversary example. Such behavior presume if we use multi-8 attack strategy to generate adversary example in the white box setting. In the gray box attack, we measure how likely the generated adversary example under a particular attack algorithm can be transferred to the defense mechanism used in the prediction. So basically here, for each row, it represents the algorithm used in generate adversary example, and the column represents the algorithm used in the defense algorithm used in the prediction. And we group the adversary example has similar L2 distance together. So here the heat map, the lighter heat map means the defense algorithm gives the better protection. Here we can clearly see RS-based method gives the best protection comparing to other defense mechanisms. So in today's talk, we give a systematic evaluation methodology based on model of adversary knowledge. Also, we show that under gray box setting, the adversary can choose a better attack strategy to generate more effective adversary examples. Also, we showed that our random spiking gives better protection compared to other defense mechanisms. You can use the following link to download the source code and run the project. Thank you for your attention. I'm willing to take your questions.